Hi everyone, very good evening. So today we are into the sort of final session on electromagnetic induction. Of course, today we have not so complicated ideas. We just have some lighter segments. So we'll just go through it. So this is where we are currently students. We are looking at the idea of self-inductance and mutual inductance. Parallelly we are also covering the inductor and inductor circuits. In fact, in session 10, right, we have covered the LR circuit with regard to DC, where you have Karthikeyan, hi, where you have a DC battery or cell connected to inductor and resistor, which are in series. This is what we have seen in the previous session. So we have the expression for the growth current. I is equal to I naught into 1 minus e power minus t by tau. This is the formula we had. Tau is equal to what? L by R, which is what we call as the time constant. Okay. So this is, and I naught will be equal to what? E by R. E is the EMF value of the cell, L is the inductance of the inductor, and R is the resistance of the resistor. Okay. So this is what we have covered in the previous session. Now what we are going to start with in this session is the concept of what we call as LC oscillations. And this one, right, we'll be covering again in little bit more detailed manner in the next chapter also. Alternating current also, just mark it. We'll cover the LC oscillations in the next AC also. Okay. So here we are basically looking at what inductor of self-inductance L, which is connected across a charged capacitor. So take a charged capacitor and connect an inductor across it. Okay. Now initially the key, this circuit will not have anything else. There will be no battery or thing. That's why it is called as what? LC. There will be no battery or anything. There will be just a charged capacitor across which we are going to connect the inductor. That's it. Okay. Now initially when we are going to close the key. So when you close the key, what is going to happen? The charge is going to flow. How? From the positive side of the capacitor plate to the, like the charge is going to, we are talking about the conventional current. So how the conventional current is going to flow? It will be flowing from the positive plate of the capacitor, and then it will be coming to the negative plate of the capacitor. So this is what we call as the discharging of capacitor. What do you call it as? The discharging of the capacitor. Okay, so here we are just going to look at the idea of LC oscillations. As I said, the LC oscillations in total, right, we'll be covering again in the alternating current chapter. Okay, so here what is going to happen? The capacitor is going to get discharged. Means the capacitor is going to lose the electrostatic potential energy, isn't it? Because the potential energy of the capacitor will depend upon the charge on it, right? If the charge on the capacitor plate is decreasing, means what? The energy stored inside the capacitor will be decreasing. But energy cannot be lost just like that, right? So what is happening to the energy? When you are establishing current in the circuit, you are adding it to what? The magnetic potential energy stored in the inductor. So first, when we are establishing current in the circuit, right, what are we doing? We are making a transfer of energy from the electrostatic energy inside the capacitor, that is losing, and it is converted into which form? It is getting converted into the magnetic potential energy inside the solenoid or the inductor. And as we will see, once the current is established, then we will see a reversal of the process, means the magnetic potential energy will be converted back into the electrostatic potential energy, and this way, right, we will see the oscillations of energy between the two forms, electrostatic potential energy to the magnetic potential energy and vice versa. That's why this is called as what? If you have the charged capacitor, okay, and we connect across an inductor, initially before you start the circuit, the key will be open, you close the key. What is going to happen? From the positive plate, the charge is going to go into the circuit and it will reach the negative plate. So this is what we call as the current. There will be a current that is established. Okay. So what is going to happen in the process? The capacitor plate is going to lose the charge. Means the electrostatic potential energy on the capacitor will be what? Decreasing, because it is losing charge, right? What is the potential energy of the capacitor? Q square by 2C formula, right? Charge is decreasing, means what is going to happen? The energy on the capacitor plates will be decreasing. But where is this energy going? The energy is going into the form of the magnetic potential energy of the inductor. Because as you see, more and more current is coming to circuit, means what is the formula for the magnetic potential energy of the inductor? Half into L into I square, right? Which means the inductor is going to have more and more magnetic potential energy. Okay. And once the current is fully established, then the reversal is going to happen. The current is going to decrease. Then we will see that the magnetic potential energy will be converted back into electrostatic potential energy. So what is going to happen is there will be oscillations. The energy is going to oscillate between the electrostatic potential energy of the capacitor to the magnetic potential energy of the inductor. How the energy is going to oscillate, we'll again explain it in detail when we go to AC. Because the same LC oscillations we will study in much more detail there. Okay. But here I just want you guys to understand the concept of what is LC oscillation. Okay. Now when we say oscillations, right, we must be able to justify that there is really oscillations. We must be able to mathematically prove that there is actually oscillation. How we are going to prove is in normal physical oscillations, right? In the physical oscillations, particularly for SHM, we have an equation. For the SHM, we have an equation. So what we are going to do is we will try to derive an equation for the LC oscillations also, and see whether it is really performing oscillations or not. That is the task. Okay. So for that, the only thing that we are aware of is what? In any electrical circuit, Kirchhoff law. So what we'll do is we'll look at one point in the circuit. We'll start from a point. We'll go across the circuit, apply the Kirchhoff loop rule. Okay. So here when we are going in the anti-clockwise like this. So here this is the current direction. Let us say current in circuit is what? I. Here I want you to look at what will be the relation between current and charge on the capacitor plate. Capacitor plate charge will be decreasing, right? Capacitor plate charge will be decreasing the way we are taking. When the current is coming from the positive plate, means capacitor plate charge will be decreasing. So minus dq by dt at any given time will be equal to our current value. The capacitor plate charge is decreasing, right? So minus dq by dt at any point of time will be equal to current value. Okay. Now when we have the Kirchhoff loop rule, so we are starting from this is the starting point. We are starting from here. We are going in the anti-clockwise. Okay. When we are going in the anti-clockwise, first we are crossing the inductor. We are crossing inductor in the direction of current. What is the potential difference? Minus L di by dt. Okay. Then we are coming like this. We are crossing the capacitor plate. How are we crossing the capacitor plate? From negative side to positive side. Remember, for a battery means if you cross from negative side to positive side means potential difference is what? Plus E. A capacitor means what is it going to be? It will be plus V. V is what? Potential difference across the terminals, the plates of the capacitor, which is equal to Q by C. Okay. So plus Q by C is equal to what? 0. Because after crossing capacitor plate, we come back to the same starting point. Okay. So the potential difference across inductor plus potential difference across capacitor plate is equal to what? 0. Now here we will try to bring the I value into the expression. Minus L di by dt can be written as what? D by dt of I. I is what? Minus dq by dt. I is what? Minus dq by dt. Okay. So minus minus is plus. This is what? D by dt of dq by dt. That is nothing but L into d square q by dt square. That is how we'll write it. In mathematics, right? We'll call it as what? Double derivative. This notation we have seen in the +1 physics also. Okay. Like d square x by dt square is equal to what? A, acceleration. Correct. So this is what? L into d square q by dt square is equal to, the q by c can be taken to the RHS. It will become minus q by c. Okay. So from here, what I am writing is, this is the important step. This is how we are going to convert this into familiar form for us. When we talk about the oscillations, right, especially the simple harmonic motion, we have a very familiar equation. Look at this. No, this one, we'll take the L to the RHS. It will go to the denominator. So d square q by dt square will be equal to minus 1 by LC into q. If you look at this equation, right, this looks familiar. Like the one equation we have in SHM. What is it? D square x by dt square is equal to what? Minus omega square into x. Do you remember this? What is this? The standard equation of the SHM in physical oscillations. Here we have a similar type of expression. What is it? D square q by dt square is equal to what? Minus 1 by LC into q. Means the charge here is going to oscillate. The charge in fact here is going to oscillate just like the way we have the physical SHM. That is how we are able to conclude that the LC oscillations will be happening. That is how we are able to conclude that the LC oscillations will be happening. But what is the main concept of the LC oscillations? Here we are going to so your question is, you are asking, will the oscillations die out? Okay, so yeah, just like the way we have the physical oscillations, right? In SHN chapter, we will study that there will be the concept of damped oscillations. Okay, similarly in the LC oscillations also they will die down. Okay, and that is what I said we will cover in detail in the next chapter. Okay, but here I just want you guys to understand the concept of what do you mean by the LC oscillations. So in AC, when we are going to discuss about the LC oscillations, right, we'll probably do the derivation one more time, but again we are going to discuss on lot of other things like how the damping will occur, what are the factors that will contribute for damping and all these things. Okay, so is it clear, guys? So this is how we are able to conclude that there will be the oscillations of charge. Okay, and so it is not like once the capacitor is fully discharged and that is it. That is the main point. So what we might think is, okay, charge is coming from capacitor, it will be fully discharged and the scope is over. It is not going to be like that. There is going to be oscillations of the energy between the electrostatic form and the magnetic form. And these oscillations, right, will be similar to our physical SHM kind of a relation. Okay, so this is what is the SHM kind of relation in LC oscillations. And we are going to have the damping and other things also in the LC oscillations, which we will cover. Okay, so in AC, right, when we go and discuss about this topic, from here itself we can tell. So from here itself, right, we can tell what is the equivalent omega value by comparing the two expressions, right? What is omega square value? 1 by LC. Omega square value is what? 1 by LC. From there we can talk about what is the omega value, and we can talk about what is the frequency of the oscillations and all these things. That and all we will discuss when we go to the alternating current. But here we just need to understand that there is going to be an oscillations in the circuit. It is not like once you withdraw all the charge and that scope is over. It is not going to be that kind of phenomena. There is going to be the oscillations of energy between the two forms. Okay. Now when we talk about the inductor, right, there is this idea of an ideal inductor. In fact, all this time when we are discussing about the inductor, we are actually talking about the ideal inductor concept. But what is an ideal inductor? See, an inductor itself is a coil. It's a coil, right? We are winding the coil on a cylindrical type of a shape or something. Now, the coil of the inductor will be made up of some material. Maybe it is a copper or it is made up of some material. Don't you think this coil also, because it is like the current is going through the coil, right? It is going to have some resistance or not? I am talking about the resistance that is going to come from this formula, R is equal to rho into L by A. If you have a coil made up of metal of some length, then isn't it going to have resistance? It is going to have some resistance, right? What is the resistance formula? R is equal to rho into L by A. But in all our discussions, right, we were actually neglecting it. We are not considering the resistance. We are not considering the resistance. When I say resistance, I am talking about the electrical resistance that will come from this formula. Electrical resistance of the inductor coil, right? We were not actually considering it. And such an inductor, right, is what we will call as an ideal inductor. So an ideal inductor, right, we assume that the wire which is used for making the inductor coil will not have any electrical resistance, significant electrical resistance. That is what we call as an ideal inductor. But when we talk about normal inductor, of course it is going to have some resistance, yes or not? So when we talk about the non-ideal inductors, the inductor coil wire itself is going to have some resistance. The inductor coil wire itself is going to have some resistance. So if you want to represent a non-ideal inductance circuit, right, we have to talk about the inductance value of the inductor and also just adjacent to that, right, like the way when you have a cell is having some internal resistance, means see how we used to represent. We'll put the cell and then we'll put a small resistance adjacent. That is how we used to represent, right? Similarly, a non-ideal inductor, right, will be represented like this. We'll talk about the inductor and also we'll express what is the corresponding resistance shown by the inductor coil wire. Okay, but in an ideal case, right, in an ideal inductor, we will not consider it. We will assume that the inductor coil wire does not offer significant electrical resistance. That is about the ideal and non-ideal inductors. Okay. Now we will come to the next idea, which is of the mutual inductance. So what is it? Mutual inductance, like remember we talked about it in I think session 8 as well as session 9. So if you have one coil and another coil, okay, so first coil of self-inductance L1, second coil self-inductance L2. Okay, first coil will have some geometrical properties. It will have its length, it will have its coil area, it will have its number of turns. Second coil also, it will have its number of turns N1, length L1. Okay, here number of turns N2, length L2. Okay, always we'll try to represent the length of the solenoid with small l. Why? Because already we have given the capital L to represent the self-inductance of the coils. Okay, and let us say the radius of the circular part is R1 here. So area of cross section is what? Pi R1 square. Here what is it going to be? Area of cross section will be, if you take the circular coil radius as R2, it will be equal to what? Pi into R2 square. So we have two inductors. Now what is the mutual inductance concept? If you pass some current I1 into coil 1, this coil 1 is going to create magnetic field everywhere. The coil 1 is going to create magnetic field everywhere. So there will be a flux. There will be a flux through the coil 2. So this is the coil 2. This is the coil 1. Okay. So flux through coil 2 because of the coil 1 current. Flux through coil 2 because of coil 1 current. Okay. If we express it as a constant M, okay, here again we will say 2, 1 means the mutual inductance of the coil 2 because of coil 1 current into I1. This formula looks similar to what we had for a single coil, right? What we said, flux is equal to what? L into I. This is the expression we had, right? Flux is equal to what? L into I. Here, flux through coil 2 because of coil 1 current. We'll express it as what? The mutual inductance of coil 2 because of coil 1, M 2, 1 into the I1. Similarly, if you pass current into the coil 2, which is I2, that is going to create a flux in coil 1. I mean, I2 will create a magnetic field around it. And through the coil 1 we can find what is the flux. So flux in coil 1 because of coil 2 current will be equal to what? Mutual inductance of coil 1 because of coil 2, M1 comma 2, into I2 because this is coming for the I2 current. Okay, now these two expressions, right, will tell how the coil 1 current is going to affect the flux through coil 2, and coil 2 current is going to affect the flux through coil 1. So in this, right, we are talking about mutual inductance of the coil 1 because of coil 2 current. Also we are talking about what? Mutual inductance of the coil 2 because of coil 1 current. While we will go through this discussion, we will see what will be the relation between these two terms, M2 comma 1 and M1 comma 2. We will see, in fact, see that these two will be equal. Okay, once we do the derivation, we will be able to see the M2 comma 1 value, right, will be numerically equal to M1 comma 2. We are going to do this derivation by taking an example. But this is what is the concept of the mutual inductance. What is the mutual inductance? We are seeing how the current in one coil will create a flux in second coil. Similarly, current in second coil will create a flux in first coil. Okay, so this is how we are going to look at the concept of mutual inductance. So what we'll see is on what factors the mutual inductance will depend upon, and like I said, what is the relation between this M2 comma 1 and M1 comma 2. Okay, what is this? This is a very simple notation. M2 comma 1 means what? The way we read it is mutual inductance of the coil 2 because of coil 1. M1 comma 2 means what? Mutual inductance of the coil 1 because of the coil 2. Okay, so we will look at what is the relation between them, but in our, at least the basic syllabus, right, what we have is a very simple example of two solenoids for the study of mutual inductance, right. The example that we are going to start with at least is two solenoids of same length, okay, which are coaxial, means they both have the same axis. You can see the axis here. This is the axis, common axis. They both have the same axis. Two solenoids, they both have the same axis and they have the same length. We are going to study the mutual inductance for these two solenoids. So if you look at the solenoids, like there is S1 and S2. S1, the radius is R1. S1 is the coil which is inside. Radius is R1 and number of turns per unit length N1. Always we are using the subscript N. The second coil, radius is what? R2 and number of turns is what? N2. Capital N1 and capital N2 correspondingly will represent what? The total number of turns in the solenoid 1 and total number of turns in the solenoid 2. So we can see the N2 value will be equal to what? Small n2 into L. Capital N1 value is equal to what? Small n1 into L. Because for both of them, the length of the solenoid is same. Okay. So for this combination of solenoids, we are having what? Two coaxial solenoids with same length. For this, we are going to talk about what is the mutual inductance. Okay. And mutual inductance can happen even if the two coils are pretty much outside, like one is here or another coil is there. These two also can create mutual inductance on one another. But our discussion is beginning with the coils which are coaxial. Okay. Now what we are going to do is we will look at the two cases. First case is what, we'll pass current through coil 1. We'll pass current through coil 1 and see what is the mutual inductance created on the coil 2. Then second case is we will pass current through coil 2. Coil 2 is, remember, the outer one. Coil 1 is what? Inner one. Okay. So we look at both these cases and see how we can look at the mutual inductance. Okay. So let us start with the first case. What is the first case? We are passing. So this is the coil 1, inner coil. We will pass a current I1. We will pass a current what? I1. Okay. So inner coil, we are passing a current I1. Now when you pass current I1, right, inside the core of the inner coil, this is the inner coil, inside the core of the inner coil, there will be a magnetic field created, isn't it? Inside the core of the inner coil, there will be a magnetic field created. What is the magnetic field created value? B1 will be equal to what? Mu naught into N1 into I1. What is the magnetic field inside? Will be what? B1 is equal to what? Mu naught into N1 into I1. Now we have to find out what is the flux through the coil 2 because of this coil 1 current that is established. Look at coil 2 now. So I'll just use a different color. Coil 2 has actually got a bigger surface area. The coil area, right, is bigger. You can see coil 2 is having bigger area because what is the coil 2 area? Pi into R2 square. But the coil 1, right, will only create magnetic field inside. Like, I'll just draw one lateral diagram, we can see. So only through this region, right, the magnetic field is created. This magnetic field is only through the inner area. The total area of the coil 2 is what? Pi R2 square. But this part, right, this part, there is no field that is created. Field is only created in the inner core. So the flux calculation, right, the area of cross section of one coil, for the outer coil, what is area of cross section? Pi into R2 square. But the outer part does not be available for the flux calculation. Why? Because there is no field at all. The field is only in the inner core because coil 1 is inside, right? Coil 1 will only create a field inside the coil 1. Means what? The flux calculation, flux will be equal to what? The field multiplied by the area. So here, what is the area that we are going to multiply with? Pi into R1 square. Why pi into R1 square? The area of the coil 2 is bigger area, pi R2 square. But magnetic field is only here. Magnetic field is only in the inner core. The remaining part, magnetic field is not there. So flux calculation, we will only be accounting for the inner area, which is pi into R1 square. Okay. And what is the total number of turns for the second coil, right? How many turns are there? N2 number of turns are there. So into N2. So the flux through the coil 2 because of coil 1 current. What is the value? Mu naught N1 I1 pi R1 square into N2. Okay, so which is what? If you write it, mu naught N1, we will write capital N2 as what? Small n2 into L. N1 N2 pi R1 square into L into I1. So if you look at this, right, remember how we are expressing the flux through coil 2 because of coil 1 current is equal to what? Mutual inductance of coil 2 because of coil 1 into the I1. So here we can see by comparing, right, what is the mutual inductance value? Mutual inductance value is equal to what? Mu naught N1 N2 pi R1 square into L. So just make a note of it now. What is it? Mu naught N1 N2 pi R1 square into L. I mean, it's a very basic thing. What are we doing here? We are looking at what is the flux. We are looking at what is the flux value. The only thing is what? When we are Sham, you're asking M2 comma 1 will be equal to M1 comma 2 if I2 is equal to I1. No, M2 comma 1 will be equal to M1 comma 2 irrespective of what is your I2 and what is your I1. It does not depend upon I2 and I1 values, right? It is not about the I2 and I1 values. It is about how the coil 1 will be able to induce the EMF into coil 2 and coil 2 is able to induce EMF into coil 1. Okay, so we can see the expression, right? M2 comma 1 is coming here. No, what is M2 comma 1 value? Mu naught N1 N2 pi r1 square into L. Okay, so here what did we do? We have seen how current in coil 1 is able to create the flux through the coil 2, and from there we got the formula. What is the formula for the M2, 1? Mu naught N1 into pi R1 square into L. Okay. Similarly, let us look at the second case. We'll pass current I2 through the second coil, outer coil. Okay. Now when you pass current I2 through the outer coil, it will develop magnetic field in the entire region. Fully it will develop magnetic field. Look at it. The full outer coil is the bigger one. No, it will develop magnetic field everywhere. Okay. What is the magnetic field value? B2 is equal to what? Mu naught into N2 into I2. Correct? That is the magnetic field developed by the outer coil. We are passing current into outer coil. Now what is our task? We have to find what is the flux through the coil 1 because of this magnetic field. Okay. So if you want to find a flux through the coil 1. Coil 1 is having a small area. It is here. Okay. Magnetic field is everywhere. But coil 1 area is what? Only small one. What is it? Pi R1 square. Only this much area will be accounted for the flux. Field is everywhere. Field is everywhere. Field is up to the outer layer. But the flux will be only accounted for whatever the area of cross section of the inner coil, because we are finding flux for what? We are finding flux for the coil 1. Okay. Means the flux for the coil 1 because of this current will be equal to what? B mu naught N2 into I2 into area. What is area? Pi R1 square into what is the number of turns of the inner coil? Total number of turns is what? Capital N1. We can write capital N1 also as what? Small n1 into L. So what is it going to be? Mu naught. You can again see small n1 small n2 pi R1 square into L into I2. This is the flux through coil 1 because of the coil 2 current. Remember the way we expressed it? It is expressed as what? Mutual inductance of the coil 1 because of coil 2 into I2. That is the formula we written, right? Now compare both of them. If you compare both of them, right, what is the M1, 2 value? Mu naught N1 N2 pi R1 square into L. If you just go back and check it, right, M2, 1 is also what? Mu naught N1 N2 pi R1 square L. What is M1, 2? Mu naught N1 N2 pi R1 square into L. So both these will give us the same value for the mutual inductance. And as I said, right, we are doing the derivation for one particular case of two coaxial solenoids. Okay. Arun, you are asking the magnetic flux outside is 0. Yeah. Outside the coil, no, I didn't get the question. Like, you're saying outside. So if you just check it, right, we are only calculating the flux through the area of the inner coil. We are not calculating the flux through the area of the outer coil. Okay, so this is how we will have the mutual inductance of both the coils proving to be equal. Now in any general case also, right, like if you have a general situation like two coils which are like differently oriented, different arrangement, the derivation of mutual inductance is going to be a little bit more complicated. But what we can know is that the mutual inductance of the coils, right, will depend upon not only the geometric parameters and number of turns, because in the previous formula, what is the formula we had? Mu naught N1 N2 pi R1 square into L. That is the formula we had, right? So there we can clearly see it depends upon the number of turns and geometric parameters. Apart from that, the mutual inductance of two coils, if you take the general situation, right, it depends upon the separation between the coils. What is separation? In the previous case, we had a very particular example, right? What is it? We had the coils which are coaxial. But if you take a general coils, the mutual inductance also depends upon what? Here we are giving this without actually deriving, okay? Because in the general cases, right, the mutual inductance derivation is going to be a little bit complicated, okay? The mutual inductance value will be depending upon the separation between the coils. Like if you have coil 1 and coil 2, when they are closer, they will be able to have a greater mutual inductance. When they are farther, the mutual inductance between them will be lesser and lesser. And also the relative orientation. Like, if you have the axis of one coil exactly aligned with the axis of other coil, the impact will be more. Okay. If they make rectangle, or the angles are right angles, like the coil 1 and coil 2, they're making, right angles with respect to each other. Then, generally what is seen is that mutual inductance will be lesser. So the two factors in general case, right, we are not giving the proof for it. This is general statement, okay. The two factors that are going to determine the mutual inductance in general case is what? The relative separation between the coils as well as the orientation between them. Orientation means what? If you take the solenoid axis, we're talking about the angle between the axis of the solenoid 1 and axis of the solenoid 2. Apart from the regular factors means what? The geometric parameters of the coils as well as the number of turns of the coils. Apart from the other geometric and other factors, right? These two also will play a role in finding out what is the mutual inductance. And we don't have the discussion of the general cases here. We are just looking at okay. See, Arun, your question is outside. So you have inner coil, right? Inner coil, you are passing current. Now, outer coil has got a total area of what? Pi R2 square. In that, this is also part of the outer coil area, right? This is also, the inner area is also part, because outer coil means what? It covers the total area. The area of cross section of outer coil is what? Pi R2 square. But in that, magnetic field, when you pass current into coil 1, right? Magnetic field is only created for how much area? Magnetic field is created only for an area of pi into R1 square. Magnetic field is created only for an area of pi into R1 square. That is why in the flux formula, right, we're only considering outer coil area is pi into R2 square. But we are not multiplying the total area of the outer coil. Why? Because for the magnetic field, it is only present in this region of pi into R1 square area. That is why we are multiplying the magnetic field with pi into R1 square. Clear? So this is about the mutual inductance general case, guys. Maybe they can get some theoretical questions on this, on what are the parameters on which mutual inductance can depend upon. But again, if you have two coils, whatever may be the geometric shapes of one coil may be bigger, one is small. Okay, one has large area, other has small area. They may be in different orientations. M1, 2 means mutual inductance of coil 1 because of coil 2 current will be always equal to what? M2, 1 means mutual inductance of coil 2 because of coil 1 current. So these two, this is like what? If you think about in force terms, we can think of it like what? The Newton's third law concept. So whatever the action, there will be equal and opposite reaction, like that. Mutual inductance of coil 1 on coil 2 will be equal to mutual inductance of coil 2 on coil 1. Okay, so this is about the idea of mutual inductance. Now, if you look at the general case where we have, say for example, there is a coil 1. Okay, it has got self-inductance L1, and there is a coil 2, self-inductance L2. Okay, in coil 1 we are saying current is I1, in coil 2 the current is I2. Mutual inductance of coil 1 because of coil 2, M1, 2. Mutual inductance of coil 2 because of coil 1. We already know that m1 comma 2 is equal to m2 comma 1. Let us call it as what? M. Let us call it as what? Simply M. So the total induced EMF in coil 1 will be, because before we come to the induced EMF, right, let me just look at the flux. Total flux in coil 1. The flux in coil 1 will be because of current I1, which is L into I1, plus it will be also coming because of the mutual inductance, M into I2. Similarly here, right, flux through coil 2 will be because of its own current, L2 into I2, because of its own current, plus the current of coil 1 also, that will come from the mutual inductance, M into I1. Is the two terms clear, guys? For the coil 1 means if you have a general two nearby coils. Why am I saying nearby? Because if you take the two coils very far away, right, mutual inductance concept will not be that much relevant. Okay, so if you have two coils which are pretty nearby, where they can have significant mutual inductance, the flux through coil 1 will be equal to what? Flux from its own current, L1 into I1, plus flux from the coil 2 current, M into I2. Similarly this side, right, for the coil 2 flux, what is the coil 2 flux? Flux because of its own current, L2 into I2, plus flux coming from the I1, that is because of mutual inductance. If you take a derivative of this, right, minus d phi 1 by dt, that is what induced EMF in coil 1, E1, will be equal to minus L1 di1 by dt minus M di2 by dt. We take a minus d phi by dt term, that's it. Similarly here, induced EMF E2 will be equal to what? Minus L2 di2 by dt, same concept, minus d phi 2 by dt, that is E2, minus M di1 by dt. Okay, so this I am trying to write down so that we will be able to conclude the entire idea of self-inductance and mutual inductance. Self-inductance is what? Induced EMF. Self-inductance is relating to what? The induced EMF in the coil because of changing its own current. Mutual inductance is what? Induced EMF coming in the coil because of changing current of nearby coils. Because nearby coils, when there is a current, right, they will produce magnetic field. Means they will be generating flux through this. If the nearby coil current is changing, means the flux generator also will change. That is the mutual inductance concept. Okay, so this is how we can see the total induced EMF. This is how we will see the total induced EMF of the coil 1 and coil 2. So this will summarize how we will look at the concept of the inductance. Inductance means what? We have to cover self-inductance as well as mutual inductance, both of them. Okay, so this is about the idea of inductance. And if you have the series combination of inductors, remember I told you that if you have series combination of inductors, right, we have L equivalent is equal to what? L1 plus L2. That time I told one thing, that the inductance, we assume that they don't create mutual inductance on each other. That is the assumption we made. Okay, so we said there will be no mutual inductance concept. Then only the L equivalent is equal to what? L1 plus L2. But if we have the mutual inductance also existing, like the two coils are nearby, then we will not be able to neglect the mutual inductance. In that case, how are we going to find the L equivalent? See, if you have the coils coupled with windings in same direction, means what? They carry current in the same direction, like this. They are coupled where they carry current in the same direction. The windings is happening in the same direction. If that is how these coils are, if that is how the coils are wound, then the L1 overall, right, will be equal to L1 plus M. L2 overall will be equal to L2 plus M. So what is our general L equivalent formula? L1 plus L2. In place of that, what we will be having is L1 overall plus L2 overall, which will be equal to what? The L equivalent value will be what? L1 plus M. Okay, L2 plus M. So the overall value will be equal to what? L1 plus L2 plus 2M. So if the windings are in the same orientation, okay, they are coupled with windings in same orientation, then L equivalent value will be equal to what? L1 plus L2 plus 2M. Okay, so even if you are not able to, clearly look at how this representation is coming, right? It is fine sometimes, at the maximum we may get straight questions where they will say there are two inductors, okay, with self-inductance value 10 Henry, 20 Henry, and the mutual inductance value is 5 Henry, like that. If the windings are in the same orientation, then what is the overall equivalent self-inductance, like that. If they are in the opposite orientation, means they are coupled with windings in opposite direction, then what we would be having is the L equivalent, right, will be L1 plus L2 minus 2M. Okay, so in that case what you are going to have is L overall for the coil 1 will be L1 minus M. L overall for the coil 2 will be what? L2 minus M. So thereby what we will get is the L equivalent will be what? L1 minus M plus L2 minus M. Totally we will get it as what? L1 plus L2 minus 2M. Okay, so these two formulae we need to remember, guys. If you have the series combination, if you have the series combination of the inductors, so when we have the windings in same manner, right, then what will be the equivalent inductance? It will be what? L1 plus L2 plus 2M. If you have windings in opposite manner, it will be what? L1 plus L2 minus 2M. Okay, and if you have the inductors in parallel, then it is going to work a little bit different manner. But for now we will just keep our discussion up to what? The series combination, which is relatively easy to comprehend. Okay, so in same manner the winding is there, means it will be what? L1 plus L2 plus 2M. In opposite manner we have winding, means what? It will be L1 plus L2 minus 2M. Okay, so this is about the inclusion of the mutual inductance, inclusion of the mutual inductance into the L equivalent formula. Okay, so we will not be able to neglect the mutual inductance when the coils are very close by and all. So we have to consider the mutual inductance also. Okay, so this is about the idea of the equivalent inductance where we will not neglect the mutual inductance part. So with this, right, now we have broadly talked about the understanding of what is the self-inductance and mutual inductance. We just have one more concept, which is the idea of eddy current and applications of the eddy current in specific cases. Okay, that I'll probably share a video on that so that you can just go through it. It's a very small concept only. Applications of eddy current, especially in electromagnetic breaks, etc. Right. So I'll probably share a video on that. That will conclude the chapter. But in terms of numericals, right, this is where we can come up to. So this is the maximum up to which we can have the numerical problems. Okay. So just I'll share that a video on the eddy currents and the applications on that. So with that, we'll wind up the chapter and make sure that you at least get some practice on problems. And if you can take some tests on the chapter, it will be well and good, because we have covered this chapter for quite some time. Okay, so we have almost nearly a month we have covered this chapter. So make sure that you thoroughly practice the problems and take the tests. Okay, we'll see in the next session.